Well, it's the nicest introduction I've ever had. Thank you very much. So, right, so as Kirill intimated, I want to talk to you today about a new way of thinking about Einstein's equations on four manifolds, but using the language of gauge theory. And so the preprint that Kirill was referring to, that grew out of joint work that I did with Dmitry Panov, and then subsequently to that, there was a much nicer version of this whole story that Kirill worked out himself, and that's the story I'm going to tell you today. And maybe if there's time at the end, I'll say where it leads to. Okay, so first of all, I just want to briefly remind you what I mean by a gauge theory. So the classic prototype gauge theory is electromagnetism, and you're interested in the electromagnetic field. But it turns out that a good idea is to consider first the electromagnetic potential. So you think of the field as being the curvature of this potential, which is a U1 connection. And then Maxwell's equations become some second-order equation for the connection. And what we want to do is we want to do something similar for Einstein's equations. But an even simpler thing, an even simpler generalization of electromagnetism is just Yangmills. And since there are going to be certain formal similarities, let me just give you a really brief review of Yangmills. So what happens in Yangmills theory, you look at, what do I want to use here? Let's say X. So you take some UN vector bundle over a Romanian manifold, and you look for a connection. So A is a compatible connection in E. And you're interested in the Yangmills energy or action, which is just, you take the norm of the curvature of A, the L2 norm of this guy, over the whole of X. So this is some interesting action that you might consider, which you can then look at the critical points. So the critical points are Yangmills equations. So the solutions are called Yangmills connections, and they solve the equation that dA star of FA is 0. So you can think of this as saying that they have harmonic curvature. So this is the analog in this situation of Maxwell's equations. But one important difference is that because this group, when n is bigger than 1, is non-abelian, this is a non-linear equation now in A. So it's a second order non-linear equation for A. Okay, so the next thing that's going to be important throughout the rest of the talk is something special that happens in dimension 4. So, four-dimensional peculiarity or special feature. Okay, so to explain this, I need to remind or tell you a little bit about linear algebra in 4 dimensions. So we're going to look at the special case where our manifold is 4-dimensional, we have a metric, and we have an orientation. Okay. So whenever you have a Romanian manifold with an orientation, you have, of course, the Hodge star, which takes p forms to n minus p forms. And in 4 dimensions, that means that the Hodge star takes 2 forms to 2 forms. Okay? And you can check also that, the square of the Hodge star is always plus or minus 1, depending on the degrees and the dimensions, but in this case, the Hodge star is actually equal to 1. Okay? So the Hodge star has eigenvalues that are either plus or minus 1, and so you can split the 2 forms up into 2 pieces, self-dual and anti-self dual. So this rank 6 bundle splits as 2 rank 3 bundles. Okay? And the reason why this is so important is because 2 forms are the home of curvature. So curvature naturally splits into 2 pieces, self-dual curvature and anti-self-dual curvature. In particular, you can do that for this connection A here. You can look at its curvature in the 2 different parts. So what's an important way of thinking about these, if you take an arbitrary 2 form, you can wedge it with itself to get a 4 form, like this, and because you've got a metric, you can compare this 4 form to the volume form. And this is just going to be the self-dual part of the 2 form its norm squared, minus the anti-self-dual part of the two form, its norm squared, times the volume form. Okay. So on the self-dual part, the wedge product is positive definite. On the anti-self-dual part, the wedge product is negative definite. Okay. So what's this got to do with Yang-Mills? So I don't want to push that off the board, so let me come over here. So what this means for Yang-Mills, well, if you look at this here, you're looking at the norm of the curvature squared. So it has two pieces, a self-dual part and an anti-self-dual part. And if one of them vanishes, then you get an absolute minimum of this guy here. So what this tells you is that the Yang-Mills energy of A is bounded below by some topological number that only depends upon E. And that this happens if and only if the connection has no negative part like this. Okay? So there's a special feature in 4 dimensions, which is a topological bound, topological a priori lower bound on the Yang-Mills energy, and that this happens if and only if a simpler equation is solved, which obviously implies, I mean, if you're at an absolute minimum, you must be a critical point, but notice that this equation is just algebraic in the curvature, so it's first order in A. So this is a sort of first order PDE for A, implying the second order one. Yeah, I might have the sign in the wrong direction and everything. So the point is that if you took the trace of FA wedge FA and you integrate this, so if Chern-Weil, do I need to tell people what Chern-Weil theory is? Perhaps? I mean, it turns out that if you just wedge the curvature with itself, so this is a 4-form with values and endomorphisms, you take the trace on the endomorphism, you get out a number. And you can check that this doesn't depend upon your connection. Because if you change your connection, this 4-form changes by an exact 4-form. So the number's independent of the connection, it just depends upon the bundle. And we can call that number, say, P1 of E. It turns out that it has another meaning in algebraic topology. It's the first Pontryagin number of this bundle. And on the other hand, this is the integral of FA plus squared minus FA minus squared times dvol. Okay? So instead of taking the L2 norm of the curvature, I've swapped the sign of the anti-self-dual part. So if the anti-self-dual part vanishes, then this is the L2 norm of the curvature. On the other hand, if the anti-self-dual part doesn't vanish, then the L2 norm of the curvature is strictly bigger, because it's got a plus here instead of a minus. Okay? So this number here, which doesn't depend upon your connection, is a lower bound for the L2 norm of the curvature. So this guy here is automatically smaller than the whole curvature. So this number that doesn't depend at all upon your connection gives you a lower bound for the L2 norm of the curvature, a lower bound for Yang-Mills. And if this lower bound is attained, then you actually know that 1/2 of your curvature vanished. This anti-self-dual piece here must be 0. Okay? So the 2 points that I wanted to highlight were the arbitrary critical points are interesting objects which solve a second-order nonlinear PDE, which looks like a generalization of Maxwell's equations, it's the Yang-Mills equations. And there's a special situation in which an actual global bound is attained, which implies a first-order PDE, because the curvature is first order in the connection, and we're just saying something algebraic about the curvature. We're saying that some component of it vanishes. So we have this first-order PDE, and the solutions of this are called instantons. Yeah, instantons. So pure thought tells you that they must solve the Yang-Mills equations because they're absolute minima. So they're obviously critical points. So somehow, psychologically, you know that they must solve this equation. But you can even prove it just directly if you didn't know about the Yang-Mills energy. So the Hodge star is equals 1 on lambda plus. So if the anti-self-dual part of the curvature vanishes, then that implies that the Hodge star of FA equals FA. Okay? On the other hand, this covariant exterior derivative, the adjoint of the covariant exterior derivative is, unless I made a mistake with the sign, you build it out of the Hodge star and the ordinary exterior derivative. Okay? So this is true always, And so on lambda plus, this guy is just equal to some, I mean, it's equal to minus the Hodge star times the exterior derivative. Okay? So now that tells you that dA star of FA for an instanton is minus star of dA of FA, and this piece always vanishes by the Bianchi identity. Okay, so even if you didn't know about the Yangmills energy or this Chern-Wei interpretation of the absolute lower bound, you could still check that the instanton equation, that the curvature is purely self-dual, it automatically implies the Yangmills equation. Okay, but we also know that from this sort of general description of it. Okay, so the key points I wanted to pull out of this were interesting action functional, arbitrary critical points solve second order PDE, looks like a generalization of Maxwell's equations, it's important in physics, the Yang-Mills equation, topological lower bound, when this is attained there's a first order PDE, which is also important, and these are called Yang-Mills instantons. Okay. So what we're going to do is we're going to do something similar for Einstein's equations. So here's an outline of what's going to happen. So we're going to start with a particular type of connection, an SO3 connection over a 4 manifold. Okay? So this is very particular to dimension 4, the story that I'm telling you today. And we're going to take an SO3 connection over a 4 manifold, and it's going to solve a certain inequality that I'll explain in a minute. Okay, so this is going to be like our electromagnetic potential, if you like. And then we're going to do some clever algebra. And then, so out of the curvature, so on the curvature, to get a metric, an actual genuine Romanian metric, GA. Okay. So then we're going to write down an action, which will just be the volume of this metric. And it'll turn out that this action has properties similar to the Yang-Mills energy. So it's going to have general critical points. So for general critical points, GA is Einstein. And that's going to be a second order PDE for A. And there's also going to be a topological bound. So, okay, what shall I put here? Some constant times twice the Euler characteristic plus 3 times the signature. So this is the Euler characteristic of the 4 manifold, and this is the signature of the 4 manifold. So they're just topological numbers that don't see the connection at all. Okay? And then this action is automatically bounded above by some positive constant that I'm too lazy to remember times these topological objects. Okay? And this bound is satisfied, so equality, if and only if A solves a first order PDE, and then, in fact, we know more about this metric. It's not just Einstein, but more of its curvature tensor vanishes as well. So then GA is what's called anti-self dual Einstein. So this is roughly what I'm going to spend the rest of the talk explaining to you. Okay? Yeah, physicists, I guess, call these guys gravitational instantons. Okay? This anti-self dual says that a certain part of the... sorry, I guess I want self-dual with my orientation conventions. Right? Yeah. No, anti-self dual. Anti-self dual, sorry. I was right all along. Okay, so this says that a piece of the curvature tensor that sends lambda plus to lambda plus vanishes. So it's an analog of this instanton equation here, but for Romanian metrics. Okay, so before I tell you about this story, I should be honest and tell you that there are also definitely disadvantages to this approach to Einstein's equations. And the biggest one that we're struggling with at the moment is that you don't get every Einstein metric this way. This is certainly a way to describe some Einstein metrics, but you don't get all of them. But we're still working on trying to squeeze more of them into the picture. But I'll come to that at the appropriate point. Okay. So kind of the sort of moral to take from this story, though, is that this metric is completely auxiliary, and the real independent variable that you should be interested in is the connection. Just like in electromagnetism, you think about the electromagnetic potential as the fundamental object from which you can build the field. But the fact that the action should be really thought of in terms of the potential, and that's exactly the situation we have here. We have some potential, A, and the equations of motions are second-order equations for the potential, right? So the connection should be seen as the fundamental object. Okay, right. So to explain how this works, I'm going to need to tell you a little bit more about four-dimensional Romanian geometry. So. Okay, so we just said that the two forms on a four-manifold split into self-dual and anti-self-dual pieces. Okay? So if you have any Romanian metric, then you can think of the curvature tensor as a self-adjoint map from lambda 2 to lambda 2. Okay, so this is true in any dimension, but obviously in dimension 4 we have this splitting into two pieces. So now I can talk about the four components of the curvature. There's a piece that sends lambda plus to lambda plus, there's a piece that sends lambda plus to lambda minus, a piece that sends lambda minus to lambda plus, and a piece that just acts on lambda minus. So the curvature tensor splits, sort of, you can think of it as a matrix if you like, A, B, C, and then by self-adjointness this B must be the dual of that one. So A here takes lambda plus to itself, B takes lambda plus to lambda minus, and C takes lambda minus to lambda minus. Let's at least make this look symmetric. Okay? And now I want to interpret the Einstein equations for the metric in terms of this block decomposition. And it turns out that this B is exactly the trace-free Ricci tensor in an appropriate sense. Okay? So Einstein is equivalent to saying that B vanishes. Okay. So you can think of this in another way. So let me just give you one sort of sanity check on this equation. B is a map from a three-dimensional space to a three-dimensional space. So it's 9 numbers. And Einstein's equations in dimension 4 are 9 scalar equations at a point. Trace-free Ricci has got 9 components. So it's at least the right number of equations. But I have a cosmological constant that's not 0. So, I mean, this I'm saying that the Ricci curvature equals some multiple. Maybe I use capital lambda times the metric. Okay, so the trace-free part of the Ricci vanishes. So Ricci has 10 components because it's a symmetric 4x4 matrix, but I don't care about the trace. So I want the trace-free part, that's 9 equations, and B has 9 components as well. Okay, so at least psychologically that shouldn't be a complete shock. Okay. So now let me give you another way of thinking about this that fits more into the story I've just been telling you about Yangmills. Okay, so what is this column here in this decomposition? Well, this is the piece of the curvature tensor that only sees lambda plus. Okay, so what this is saying for you is the following thing. If you have a Romanian 4-manifold, you have this SO3 bundle lambda plus. So this is an LSO3 bundle. It's a rank 3 bundle with a metric. And you have the Levi-Civita connection on it. Okay, so on any Romanian 4-manifold, you have an SO3 connection on lambda plus, it's just the Levi-Civita connection. And what this equation says is that this guy is a self-dual instanton. Okay, so Einstein is equivalent to this guy being a self-dual instanton. So this is the first hint that Einstein's equations in dimension 4 are really a version of gauge theory. Okay, because you're actually looking for a connection which is an instanton. But the problem is that you already know the metric. Okay, so it's a coupled problem. You're looking for a connection and a metric that makes the connection an instanton, and also the connection is at the same time the Levi-Civita connection of the metric. Okay? So we're not yet purely in the world of connections. Okay? How to find Einstein metrics in the set SO3 connections which are instantons for some metric. Okay. Okay, in particular, it would be very nice if, when I gave you a connection in this set, you could recover the metric. Okay, suppose I give you a connection that's in this set, can you recover the metric from it? Doing that will be this step of the process. Okay, this clever algebra that you need to reconstruct the metric out of a connection. So that's the next thing that I want to explain. So having turned my phone off to not interfere with the microphone, I now have no idea how long I've been going. Okay. Okay, so conformal geometry in 4D. Okay, so the first thing to say is that actually up to now, when I've been talking about this bundle lambda plus, I always fixed a metric and an orientation. But in fact, I didn't need to fix the metric because it turns out that if I multiply my metric by a function, they have the same bundle of self-dual 2 forms. And the reason for that is very simple. It's that in any dimension, the Hodge star in the middle dimensional forms is conformally invariant. Because if you think of the definition of the Hodge star, you wedge 2 forms together and you divide by the volume form. But in middle dimension, everything scales with the right weights, so that actually the Hodge star of this guy on lambda 2 is equal to the Hodge star of this guy on lambda 2. Okay? Hodge star is conformally invariant in the middle dimension, and so the lambda plus and lambda minus don't see the metric, they only see its conformal class. Okay? So when I talk about an instanton, I really only need to fix a conformal class. Okay? So the first thing I want to tell you is there are some connections from which you can recover a unique conformal class that makes them an instanton. Okay? So how does that go? So let me just remind you of something that I said a minute ago. So if you have a conformal class, so conformal class of metric, out of this conformal class of metrics, I can build my lambda plus, and for all alpha inside lambda plus, the square of alpha is positively oriented. Okay? It's a positive multiple of the volume form. Even though volume form doesn't make sense for a conformal class, positive multiple of volume form does. Okay? So if I have a conformal class, I get some rank 3 subbundle of lambda 2, and this rank 3 subbundle has a special property that all of the forms in it have positive square. Okay? Now it turns out that you can reverse this arrow. So if I have a rank 3 subbundle of lambda 2, and for all alpha in V, the square of alpha is positive, then there exists a unique conformal class with V equal lambda plus. Okay? So conformal class gives you a bundle of self-dual 2 forms enjoying some algebraic property. And what's important in 4 dimensions is that, in fact, you can reverse this. Whenever you have a rank 3 subbundle that has this important algebraic property, then, in fact, it is the bundle of self-dual 2 forms for some conformal class, which is uniquely determined. Okay? And, again, you can see that in terms of this dimension count that I spoke about over here. If you vary your conformal class, you're varying your bundle lambda plus. Okay? So a rank 3 subspace of a rank 6 space, that moves in a rank 9. 3 times 6 minus 3, so that's 9. So there's a 9-dimensional space of 3 planes inside lambda 2, and this condition is open. So there's a 9-dimensional space, and varying your metric up to conformal class is adding on a symmetric trace-free tensor to it. So there's a 9-dimensional space there. So at least infinitesimally, you can believe this statement. Okay, so to discover a conformal class, what we need to do is find a rank 3 subspace of lambda 2 which has this algebraic property. Okay? But if we start with a connection, then we're already in good shape. So let me explain how that part goes. I guess I can go over here. So now let's just take any SO3 connection over a 4 manifold. Okay? And now I'm going to try and produce out of this SO3 connection a rank 3 bundle that looks like this. Okay? So I'm going to look at the curvature of A, and I can locally write it as a triple of 2 forms. So this EI is a local frame of the Lie algebra bundle. So little SO3 has rank 3. So I choose some local frame for this bundle of Lie algebras. The curvature is a 2 form with values in Lie algebras. I get 3 2 forms. Okay? So when is the span of these guys inside lambda 2 definite? So let's call these guys definite. Let's call such a V definite. So this is an inequality on the curvature, and it just says that if I wedge these 2 forms together, I get a matrix of 4 forms, which I can write as Mij times some fixed reference form, and Mij should be positive definite. This is the same. So happens if this matrix is positive definite. So whenever that happens, we'll call our connection definite. So for such A, call such an A a definite connection. So now let's see what we've done. We started with a connection. It solves this curvature inequality, that the curvature 2 forms wedge together to give a positive definite matrix of volume forms. And this curvature inequality tells us that the span of these 2 forms is lambda plus for a conformal class. So if I have a definite connection, it gives me a conformal class, and it's the unique conformal class that makes this guy an instanton. It's the only one for which these guys are self-dual 2 forms, by definition. Okay, so I'm getting dangerously close to having to use your board cleaning. So A definite, we build a conformal class of metrics for which A is an instanton. Okay, so we still haven't right. We still haven't built a complete metric, and this bit's a little bit harder to motivate. So now we need to define a volume form. So So to think about the volume form, let's just go back over here to this equation here. Okay, so every time I chose a volume form, I got a symmetric matrix. Okay, positive definite symmetric matrix. If I double the volume form, I halve the symmetric matrix. Okay? So choosing the volume form is fixing the scale of this matrix. Okay? So what am I going to do? I'm going to do it like this. Okay? So the first time you see this, you might think, well, why? And then I'll try and explain why. So we're going to choose our volume form. VA is defined so that the trace of the square root of the corresponding matrix equals 1. Okay. I suspect Kira will be happier if I put modulus of lambda here, but let me just put 1. Okay. So why have I done that? Okay. So remember what we're trying to do. We're trying to find Einstein metrics by first of all writing down a connection, secondly realizing it as an instanton for some conformal class, and thirdly, we're going to hope that we can find out how to recognize it as the Levi-Civita connection of the metric that we wrote down. Okay? So let's just suppose that we'd started with an Einstein metric. So suppose we start with an Einstein metric. And we take A to be the Levi-Civita connection on lambda plus. Okay. So if somewhere there's that block description of the curvature tensor, so you remember the curvature tensor of our metric G split into these pieces. Einstein says that these vanish, and this piece here is the curvature of lambda plus. Okay, so the curvature of this connection is just this matrix A. Okay, and actually you can check that what you get for M is A squared. Okay, so remember, to get an M I needed to pick a volume form, and I'm obviously going to use the Einstein volume form, the volume form for this metric. So the square root of M is just A, assuming A is positive definite. If A is negative definite, then I should take minus A. Okay, but let's just assume for the moment that A is positive definite. So I want the trace of A to be 1. So we're asking, what's the trace of A? Well, if you look at the trace of A, what have I done? I've taken the curvature tensor and I've produced a function. And there's only one function that I could possibly produce in an invariant way out of the curvature tensor. This has to be the scalar curvature. Okay, so by using the Romanian volume form, I've arrived at trace of A as a function which is constant. So what I should be doing with my connections is I should be picking the volume form that makes the trace of the square root constant. In this case, 1. So, okay, so as I said before, there was an ambiguity. If A was negative definite, then I should have taken minus A here. So really what I should be doing is I should be taking the trace of the square root of A squared, and then I will get the absolute value of the scalar curvature. And that's why this number should be positive. Okay, so if I'm to have any hope of hitting Einstein metrics with this game, that's the normalization I should take. And I've normalized things so that, I mean, perhaps this is scalar curvature over 4 or something. I think it is. Up here? Oh no, but I want to take the positive square root, so it better be 1. Yeah, I mean, it depends on where you hide the sign, and I've hidden it here. And I think that this might be scalar curvature over 4. But anyway, this game here is what you have to do if you want to hit Einstein metrics that look like this. Okay, it's the choice is forced upon you. Okay. Okay, so we've seen now how to take a definite connection and build out of it a Romanian metric. And now we want to know, when is that Romanian metric Einstein? What sort of equation does this give us for A? Okay, all right. So So we started with A, and we built from this a metric GA with our volume form VA, making A an instanton. On the other hand, we also know that an Einstein metric has the connection on lambda plus as an instanton. Okay, so can we recognize this as lambda plus, as the Levi-Civita connection? So when is A the Levi-Civita connection of G? So that's the big question. If it were equal to this, then we'd know we were done, because this guy is an instanton. So the Levi-Civita connection of GA on lambda plus will be an instanton, and that tells you that the metric's Einstein. That's the game you want to play. Okay? But there's a subtlety here, which is that A was an arbitrary SO3 connection on some bundle, some SO3 bundle over your 4 manifold, and this guy is a connection on a different bundle, lambda plus. So we need to, first of all, we need to identify the two bundles before we can compare the connections. Okay? So I need to identify SO3 bundles. So the auxiliary SO3 bundle and lambda plus, which of course depended on, I mean, we first of all started with a connection on a bundle. We didn't have a metric. We didn't have a lambda plus. And out of the connection, we built a lambda plus. And this bundle lambda plus isn't necessarily the bundle we first thought of. We need to identify them before we can compare these two connections. Okay? So how are we going to do that? Well, we're going to go back to this. You can think of these EIs. They're a local frame for your Lie algebra bundle. But instead, you can think of them as a local frame for the actual vector bundle. So if I give you a vector in R3, it also gives you a generator of rotations, just rotations around that vector. Okay? So I can think of this EI simultaneously as being a local frame of this original bundle. Okay? And now this curvature is giving you an identification between the bundle you first thought of and your bundle of lambda plus. Okay? For each vector, for each basis vector, I'm getting another basis vector in lambda plus. Okay? But there's a problem. These curvature forms aren't orthonormal. Okay? Because of this. Okay? This matrix is exactly telling you how they fail to be orthonormal. Because on self-dual 2 forms, the wedge product is the inner product. That's how we set things up. Okay? So if I just use the curvature to identify E and lambda plus, I won't get an isometric identification between the two. So I actually need to twist the curvature by something to get this isometric identification. And that's what I'm going to do. Okay? So I'm going to write phi I to be m. I take the positive square root of m, ij, and I'm a mathematician, so I'll write a summation sign, fj. Okay? So these guys are now orthonormal because I've corrected for the fact that the f's weren't by pre-multiplying by the square 1 over the square root of their inner products. So these guys, this is an orthonormal frame of lambda plus. Okay? And so now I can write down this guy, phi a, which is just this m to the minus a half of f a, which is just this sum, locally it's summation phi I ei. I can think of this capital phi as being an isometric identification of E and lambda plus. So it takes elements of E, gives me elements in lambda plus, and it's an isometry. So now I really can compare A, which is a connection on the bundle I first thought of, with the Levi-Civita connection of its metric, which is a connection on here. Okay? So I push A forward using phi, and I'll get a metric connection over here. Okay? So when is it the Levi-Civita connection? Well, now you just have to remember what's the Levi-Civita connection. It's the unique metric connection in this bundle which is torsion-free. Okay? Well, you're probably more used to seeing that with this replaced by the tangent bundle or the cotangent bundle, but the same fact is true for this bundle of self-dual 2 forms. Okay? So we just need to ask, what's the torsion of this guy? Okay? So perhaps I should remind you what the torsion of a connection in lambda plus is. All right, so I can take a section of lambda plus, and now I'm just going to talk about any connection. Let's call the connection B. Okay? So if I differentiate it with B, I get a section of lambda 1 tensor lambda plus, okay, where this is the additional factor that sees the derivative. And then I can just skew symmetrize to get a section of lambda 3. Okay. So let's call that, I don't know, sigma. So now I can look at sigma done after B, and I can subtract the ordinary exterior derivative, because these are just two forms. I take an exterior derivative of the 2 form, I get a 3 form. And this guy is a tensor, and it's just the torsion of B. And it lives in lambda 3 tensor lambda plus. So it eats elements of lambda plus and spits out elements of lambda 3. Okay. And the Levi-Civita connection is the unique connection on lambda plus, which preserves the metric and for which the torsion vanishes. So the question now just becomes, what's the torsion of this connection? Okay. I need to write down a 3 form with values in lambda plus. Okay. And there's an obvious guess. So if I take the torsion of this guy, it's a 3 form with values in lambda plus. Well, this phi, just like curvature was a 2 form with values in E, so is phi. It's just a twist of this 2 form. So phi is a 2 form with values in E. So I can take its exterior derivative and get a 3 form with values in E. Okay. But E is isomorphic to lambda plus. These are the same space. Okay. So if I identify E with lambda plus, the torsion is just this. Okay. So when this vanishes, A is the Levi-Civita connection. So if A is a definite connection, and dA phi A equals naught, then GA is Einstein. So there's one thing that's quite remarkable the first time you see this. What was phi? Phi was built algebraically out of the curvature. So phi is first order in A. So dA of phi is second order in A. This is a second order PDE for your connection. On the other hand, your metric already depended to first order on your connection. So you might think naively that Einstein's equations will be third order in the connection. But they're not, they're second order. So we've already made some gain. We've hidden something somewhere. Okay? The second thing to notice is that this looks a little bit like the Bianchi identity. Okay? Except rather than the curvature, I've had to twist the curvature by this matrix M. I had to twist this curvature form. But if M actually was already the identity, I mean, remember that we fixed the trace of the square root to be 1, so I guess M had better be 1/9 times the identity on E. So if this matrix was a constant multiple of the identity, then phi A equals F A, and then dA phi A automatically equals naught. Okay? By the Bianchi identity. But this is a first order condition in A. Okay? And this first order PDE implies that GA is Einstein. But if you trace back through everything that I said over here, this actually implies, so in this case, GA is Einstein, and it's also what's called anti-self-dual. So I've just realized how bad my notation is. What does it mean? It means that this matrix, this box here, the top left box, it's not just any old 3×3 matrix, it's a multiple of the identity. So the trace-free part vanishes. And the trace-free part of this is part of the Wahl curvature. So in other words, when M is a multiple of the identity, you have what Kirill calls a gravitational instance on. So this is second order PDE. And this is first order PDE. So we're looking a little bit like Yangmills theory. The general critical points solve a second order PDE, but there are some special, the general equation is second order, but there are some special solutions which solve a first order equation which implies the second order one. And what's missing is the action. Okay, so how long have I got left now? 15 minutes, wow. I feel I've gone too quickly. Okay. So I normally call this Krasnov action, but then he's going to blush. Okay, so this is due to Kirill. I mean, other parts of this story were also due to Kirill, but I think this is the most impressive bit. Okay? So let's set S of A equal to the integral of this volume form. So it's just the volume of the metric. Okay. So here's the theorem. A is a critical point of S if and only if dA phi A equals naught. So this is exactly the Euler-Lagrange equations for this action. Okay. Just like in the Yang-Mills case, critical points solve some second-order PDE, which gives you interesting equations of motion for your field. Okay. Moreover, this action is bounded below by some topological constant, as I was talking about before, with equality, bounded above, sorry, in my conventions, with equality if and only if you have this M being a multiple of the identity. Okay. So, just like in Yang-Mills theory, there's an a priori topological bound of your action, and you attain it exactly when you solve a first-order PDE, which obviously then implies your second-order PDE. So in this whole story, you should be thinking of Einstein's equations as being the analog of Yang-Mills equations, and you should be thinking of anti-self-dual Einstein equations as being the analog of the instanton equations. So that's kind of, I mean, that's kind of the story as you would tell it if you were a salesman. But now I have to come to the slightly depressing part, which is which Einstein metrics have we got in this whole picture? Okay, so this is the kind of the bad news. Right, so it all comes down to this block decomposition that I keep writing. So this I've used A for this thing here, but it's also the connection. So let me actually tell you what it is. So it's the self-dual Wahl curvature plus the scalar curvature divided by 12. And then here was the trace-free Ricci, at least the adjoint, and here was the trace-free Ricci. And then here you have the anti-self-dual curvature, Wahl curvature. Okay, so this is the block decomposition here. Okay? And we were looking for Einstein metrics, so we already knew that these two pieces vanished. And we were only looking at lambda plus, so we don't care anything at all about W minus. Okay? But there's a condition on this that enables this Einstein metric to show up. So we only get Einstein metrics with W plus R over 12. So this is an endomorphism of lambda plus, and it either has to be strictly positive definite or strictly negative definite. So these are the only Einstein metrics we can see. So now you might ask, well, how many are there in existence in the world already known today? Okay, and this is the bad news, but it's not quite as bad as it sounds. So examples. Well, there's the force sphere. So I'm going to talk only about compact examples. Okay, so there's the force sphere. There's also CP2 with the Fabini-Studi metric, but in this whole game I've picked an orientation to talk about lambda plus, and CP2 has a natural orientation coming from its complex structure, and if I want the stories to tie in, I should take the opposite orientation on CP2. Okay? So you also have hyperbolic manifolds and complex hyperbolic. And again, complex hyperbolic manifolds, they come with a natural orientation, but if I want this to tie in with lambda plus and not lambda minus, I should take the opposite orientation. And these are just the negatively curved joules of these two examples here, but there's only two compact examples here, whereas there are infinitely many in each of these cases here. Okay? And I'm afraid there my list has to stop. Okay? So these are the only known examples to date. Okay? So big question. Are there any more? Right, so that's now why this news is not as bad as it first looks. Okay, so what are we missing? So we're missing the following metrics. Okay, so obviously we're missing flat space because everything's 0 then. So we're missing, if we're talking about compact metrics, flat metrics on the 4 torus. We're also missing Kähler-Einstein metrics. So in particular, the Ricci flat metrics on K3, we're missing those. But we're missing anything that's Kähler because the Kähler form is parallel. So it gives you something in the kernel of this endomorphism here. So you might be slightly worried. These two guys, they're both Kähler. Okay? So how did I escape that problem? Well, Kähler-Einstein metrics, we're missing them if we consider the complex orientation. And here I switched the orientation. Okay? But arbitrary Kähler-Einstein metrics we're missing. And what else are we missing? So let me write down other Einstein metrics. Okay, well, there's a special metric on CP2 connect sum CP2 bar called the page metric. And there's a special Einstein metric on CP2 connect sum 2 copies of CP2 bar called the Chen-Lebrun-Weber metric. So Page found this metric in the 70s. Chen, Lebrun, and Weber found their metric on the double blow-up of CP2 in about 2008. I guess end of the 90s, start early 2000. There's a sequence of metrics due to Anderson on Dane fillings. Of hyperbolic metrics, hyperbolic cuspidal metrics. So you take a hyperbolic manifold that's not compact. So it has these hyperbolic cusps, and you fill in those cusps by gluing in a particular metric, and then you perturb that metric to get something that's Einstein. So this gives you an infinite family of Einstein manifolds. And I think that this is it. This is the complete list of known compact Einstein 4 manifolds. So the fact that we've only got these ones, I suspect, is not due to the fact that our theory forces you to have locally homogeneous metrics. It's more that we just don't know many examples of Einstein metrics. Okay? Which brings me to what this might be good for, this whole setup. I mean, if you're a physicist, you probably don't need to be convinced of the fact that it's exciting to have an action whose critical points are Einstein metrics. Okay? But for a mathematician, you might want to use this to do something. You might want to use it to find new Einstein metrics. So hope for the future. I feel this pen is running out. So find Einstein metrics. So what would you have to do for this? You'd have to start with a manifold that has a definite connection, okay? In order that you know that this theory isn't empty. And then you try and maximize the action and hope that you get stuck somewhere at a critical point of the action and that you found an Einstein metric. So the good point here is that there are certainly examples. So there exist examples of definite connections on manifolds where no one knows if there's an Einstein metric or not. So these guys are a good test case for the whole game of trying to hunt for new Einstein metrics. So the second thing that you could be thinking to yourself is, well, this seems an extremely complicated story to find Einstein metrics. We don't even get all of the Einstein metrics, and yet all along I already knew an action functional whose critical points were Einstein metrics, the Einstein-Hilbert action. Why don't you just go away and use that? Okay, so it looks more convenient than the Einstein-Hilbert for the following reason. So I'm going to assume you already know what the Einstein-Hilbert action is. Is that fair enough? Okay, and now I'm going to tell you why it's quite awkward to actually use it. So what happens with Einstein-Hilbert is that an arbitrary critical point of Einstein-Hilbert, an Einstein metric, is a saddle point. And here I've drawn a saddle. And the problem is, it's not just a saddle, it's got an infinite dimensional negative space and an infinite dimensional positive space. Okay? So the Hessian has infinitely many eigenvalues of both sides. Okay? So if you ever try to find this just by using some sort of min-max procedure, you're in all manner of trouble. So here's the best that people have done. So you can notice, first of all, that there's a geometric interpretation of these negative and positive directions, okay, at a critical point. And that's that the positive directions, these vary within the conformal class. So these keep conformal class fixed. And these change sort of transverse to conformal. So here's how your min-max might go. In a given conformal class, you try and minimize Einstein-Hilbert. And that gives you a metric in each conformal class. And now you try and maximize Einstein-Hilbert for those particular metrics as you vary the conformal class. Okay? So the first half of this problem has been done. And even that was a major triumph in the theory of PDEs. You can minimize the Einstein-Hilbert in a fixed conformal class. And this is the solution of the Yamabe problem. So the Yamabe problem, so Rick Shane proved this. Shane's the solution of Yamabe problem. So can minimize in a given conformal class. But now you have a problem, which is that the solution to this minimizing problem is not unique. In other words, as you move the conformal class around, there might be two solutions. And one of them goes to the Einstein metric and the other one disappears. How do you know that you're following the right one? In other words, the failure of uniqueness to this solution tells you that there's no compactness theorem for solutions to the Yamabe problem. As you're moving the conformal class and you're keeping your eyes on the Yamabe minimizer, it might just disappear. Okay? So you can't carry out min-max. So as yet, as far as I'm aware, no one has been able to use min-max and Einstein-Hilbert to actually prove the existence of an Einstein metric. Okay? What's good here is that this just doesn't happen. Our action at a critical point has only finitely many positive eigenvalues. And indeed, we even know that for anti-self-dual Einstein metrics, it's got no positive eigenvalues because you're at a maximum. Okay? So sort of this guy, sort of S has elliptic Hessian. So from the completely naive point of view, so finitely many positive eigenvalues. So from the completely naive point of view, it already looks more convenient than using Einstein-Hilbert to find these new Einstein metrics. Okay, so have I finished my time? No? A few more minutes. Okay, so there's one thing that I've been hiding from you throughout the whole talk that I should probably tell you, and it's kind of the difference between positive and negative curvature. Okay? So in Romanian geometry, positive and negative curvature, they're obviously massively different. Okay? And somehow, it was only right at the very end when I was giving you examples that you first saw this sign on the curvature tensor. Okay? But in fact, the sign's present all the way from the beginning in the whole story. So let me just explain what this is. So, sign of a definite connection. So remember that a definite connection is just an arbitrary SO3 connection on some auxiliary bundle. And normally, for any old connection, you can't give its curvature a sign. If you think about how you talk about the sign of the curvature tensor of a Romanian metric, it's critical that the curvature is of a connection that's on the tangent bundle. Okay? But in this case, it's just any old bundle. Okay? Except we've just seen that the bundle's isomorphic to lambda plus. And that means that you can give a sign to the curvature of a definite connection. So let me just repeat how that goes. Okay, so what were EI? They were orthonormal frame of little SO3. Okay? So it turns out that little SO3 is a rank 3 vector space, but it has a natural orientation, in the same way as complex vector space has a natural orientation. And a kind of cheating way to do it is to say that E1, E2, and E3, so if I give you E1 and E2, then I need to tell you so these guys are orthonormal, I need to tell you a vector at right angles to both of them that completes this in a positive or oriented way, and I'm just going to take their Lie bracket. Okay, so this is oriented. Okay. Similarly, these guys, these FIs, they live in lambda plus, okay, like this, and so. Right, yeah, because A is definite. So A is definite. Otherwise, I can't define a sign. Okay, but when A is definite, I can define a sign. These guys live in lambda plus of G of A. Okay, this metric that's associated to A. And now, what do I want to say? Okay, well, let's even use the corresponding phi i's, right? All right, so this is an orthonormal basis. Okay, so these guys are two forms, but if I raise an index with the metric, I can think of them as endomorphisms. Of the tangent bundle. Okay? So I have an orthonormal triple of self-dual two forms. I raise an index, I get a triple of endomorphisms, and you can check that the fact that these are self-dual and unit length means that these endomorphisms square to -1. Okay? So they look like multiplication by I. And I've got 3 of them. So I can ask, do they solve the quaternion relations or not? Okay, so if J1, J2, J3 quaternionic, we say that A is positive definite. And if minus J1, there are 2 possibilities. Either the J's do or the minus the J's do. Then we say that A is negative definite. And it turns out that if you start with a positive definite connection, you can only ever end up with a positively curved Einstein metric. And if you start with a negative definite connection, you can only ever end up with a negatively curved Einstein metric. So you know in advance, even before you've found a solution to Einstein's equations, what sign the curvature can be. Okay, so now let's come back to these examples. So it turns out that if you're a positive definite connection and you solve the field equations, if you give an Einstein metric, then it's a theorem that the only examples are these two here. So the only positive definite connections solving the field equations come from these. So we're never going to find any more positively curved examples than these in this theory. On the other hand, these examples that I mentioned, these examples up here, obviously these are all negative definite. And it seems that there are lots and lots of negative definite connections. So to look for new Einstein metrics, we should be looking in the negative definite case. Okay. On the other hand, just to finish, just one last comment. Suppose we could play this game in the positive definite case, this calculus of variations. You give me a positive definite connection, and I know that I can maximize this action and find a critical point. Then from what I just told you, I know that the 4 manifold that we started with is the 4 sphere or CP2. So that would prove a kind of gauge-theoretic sphere theorem. So sphere theorems in Romanian geometry have a long history, and they all start along the lines of, I give you a manifold with a metric whose curvature satisfies a certain inequality. And lo and behold, the manifold I gave you must be diffeomorphic or homeomorphic to the sphere. Okay? This would be a gauge-theoretic kind of sphere theorem. You give me a manifold with a connection whose curvature solves an inequality, namely it's positive definite, and then I play this game over here with the action, I find an Einstein metric, I can check the Einstein metric must be the one on 4 sphere or CP2 bar. So you could only have given me the 4 sphere or CP2 bar to begin with. Okay, so that kind of rounds off my hopes for the future, and it's probably a good place to stop. Thank you very much. Yeah.
And in some sense, from solution of this first order PDE,
Mm-hmm.
you can find or you can describe the relevant solution for initial Yangmills equation. Correct?
Not quite. What I was more saying is that there's a first order PDE that if your connection solves it, then it automatically solves the Yangmills equation. It's a bit like a square root of the Yangmills equation.
Yes, but generally speaking, to solving of first order PDE is much simpler test.
Yes. Much more is known about instantons than Yangmills connections. That's true.
And, okay, finally, let me, I would like to understand. You may construct this first order PDE in explicit form, or
Mm-hmm.
you claim that there exists such first order PDE.
No, it's an explicit PDE. Yeah.
Explicit. And linear?
No, nonlinear.
Okay.
Yeah.
Okay, thank you.
You're welcome. I mean, it's non-linear, but the non-linearities are in zeroth order.
Sorry?
It's non-linear, but the non-linearities are in zeroth order. It's like derivative plus object squared. It's quite a simple. From the point of view of nonlinear PDE theory, it's quite simple. Its non-linearities don't look too complicated. But it's a much studied PDE in four-dimensional geometry. Just that first order PDE itself.
Okay.
Now, do you know that there is no Einstein metric set CP2 and for which
I don't, no. I don't. The problem is that all of these metrics, apart from on the 4 torus, it can't work. Because 2 chi plus 3 torus 0. But none of these Kähler-Einstein metrics are explicit. So you can't look and see what their W minus plus S over 12 looks like. I mean, you've got no hope. If you see what I mean. They all come from an abstract solution. There's an abstract theorem that says you can solve a complex Monge-Ampère equation. But you don't know what the solution looks like. So, yeah, there's definitely recent work on numerical computations of these metrics, but I don't know if anyone has computed enough about what the Antiself dual curvature looks like for me to be able to say. I mean, it's possible that there are some in there somewhere, just in the same way as you get these guys, right? But I don't know. I mean, I think that they tend to spend more time looking at K3 because physicists are interested in K3. And K3, again, it can't work because 2 chi plus 3 tor vanishes. Although I'm hesitating now because 2 chi plus 3 tor vanishes for the complex orientation. Maybe it doesn't vanish for the non-complex. I don't know.
But in principle, you could check the things that really different computations and run some more computations.
Yeah? And see if indeed, I mean, I guess if it were definitely positive, you'd be able to prove that it was positive, even with numerical approximation. Because you'd know that your approximation was accurate with an epsilon and it had lowest eigenvalue 5 epsilon or something. But I mean, one reason why I think it might not work in general is that one of the ways to build a K3, you take the 4 torus, you divide by Z2, and then you glue in tiny Iguchi-Hansons. And this metric is flat almost everywhere. And then you perturb it to make it Ricci flat. So where it's flat almost everywhere, it's very hard to believe that as soon as you perturb it, W minus becomes non-zero everywhere. But that's K3. So, but it's definitely worth thinking about, yeah.
Yeah, sorry. I didn't understand what the significance of starting with an SO3 connection was, and if you started with some other connection, if you could somehow run through the same arguments and get some new types of metrics.
I think you have to start with an SO3 connection for the following reason. What we're trying to do is we're trying to spot an Einstein metric by virtue of the fact that its Levi-Schifferter connection on lambda plus is an instanton. But lambda plus itself is an SO3 bundle. So we're trying to spot the Levi-Schifferter connections in the space of all connections which are instantons for some metric. So we should start with SO3. A kind of even more naive way where is the formula? Somewhere, I must have it. Even more naive way is you're trying to, you want the image of the curvature, you want these two forms to be a lambda plus. So there can only be 3 of them. Right? You might, if you like, look at, right, so one thing you can do is you could look at triples of U1 connections on line bundles. Then you'd have 3 curvature forms, and you could play this whole game. But then, I mean, then you get something slightly different, because the connection that you pushed across, wherever I've written it down, right at the top of there, the connection I'm pushing across, it isn't really A, it's the connection on the bundle of Lie algebras. Okay, and if you push across the connection on the bundle of Lie algebras from a triple of U1 connections, it's flat, because U1 connections, their Lie algebra bundles are trivial. Okay, so you would, if you played that game, you would get hypercalometrics. So it's true, there is a slight variation of this story, where instead of looking at SO3, you look at T3. And then instead of these anti-self-dual Einstein metrics of non-zero scalar curvature, you get as critical points hypercalometrics. That's true. Yours will work as well, I think, yeah. But, I mean, in that picture, almost any action principle will work because, for example, the one I used in that preprint, that works as well because you can prove that there are no intermediate critical points. You can prove that the only critical points are the first order solutions, just like we have in the positive definite case here as well. So. What goes wrong? Okay, maybe the easiest one to talk about is the page metric. So this metric here. So let me draw the page metric. So you start with a 3-dimensional sphere and cross an interval like this to make a 4-manifold. And as the sphere moves along, you change. I mean, you can think of the sort of, there's an invariant framing of the tangent bundle of the 3-sphere given by just 3 different covectors, and you just change their lengths as you move along this guy here. You shrink 1 and you keep 2 the same, so 2 with non-zero length, and it collapses to an S2 at one end, and it collapses to an S2 at the other end, like this. So you have this family of 3 spheres, and at each end it collapses into an S2 in different ways. And this is what's giving you the CP1 that sits inside one of these CP2s, and the CP1 that sits inside the other one. Okay. And it turns out that if you look at the Levi-Civita connection on lambda plus, then over this whole region here, it's positive definite. And then at this point here, 2 of the eigenvalues of that matrix M go to 0. Okay, so you can look at sort of M to the half, and over here, call this. Suppose its eigenvalues are lambda 1, lambda 2, and lambda 3. Then over here, all the lambdas are positive. And over here, lambda 1 is positive, and lambda 2 and lambda 3 are now negative. Okay. So if you just stare at this connection, you can't really write down the metric, because something singular happens here. Except you can in a way, because the metric wasn't built from the curvature, it was built from this guy phi, which I've lost now. So this twist, so phi is m to the minus a half times f. And where the f's vanish, the m blows up. So this guy does extend smoothly. So that's how we're hoping to include other Einstein metrics that have this sort of singular behavior from the point of view of the connection. I mean, the metric's completely smooth. There's no problem from the point of view of Romanian geometry, but we're seeing a singularity because we're determined to look at it through the definite connection picture. Okay? But as soon as you move to the phi, the singularity disappears. As you know it must, because the metric's smooth. So the question is how to interpret this without knowing in advance that this is smooth.